sur Zoom, sur YouTube. Donc, ça va démarrer bientôt.
Exposé en français ou en anglais?
Nous, en
Elle
anglais.
parle en français, évidemment.
Mais nous, en anglais.
En anglais,
Je
parce
suis
que
incapable de parler français.
c'est pas si mal, hein?
Non, pas pour des choses techniques.
D'accord.
Ah, je plaisante. Je plaisante. Voilà, écoute, Alejandra, c'est un plaisir, comme toujours, de te voir et de parler avec toi. Et donc, tu vas nous expliquer comment on fait pour arrêter le sida. Non, pas le sida, c'est pas le sida, c'est le Covid. C'est bien. Voilà.
Donc, je remercie Paul encore une fois. Et from now on in English. But I'm going to, let me get the screen bigger, I guess. Can I do that? Yes. Okay. So what I'm going to do today is more related to things I've done than what I told last week. So it's based on things that I've been doing lately with this bunch of people from Politécnica de Catalunya, my own university, Harry Joe, who is in British Columbia, David in University of Barcelona, and Pere Puig in Autónoma with me as well. So let's go. Okay, what I'm going to tell you is what we have been doing with underreporting of count time series. That is, most of public health phenomena are traditionally underreported. You have less cases reported in the official data than what you really think there exist. That happened with coronavirus in particular at the beginning, when there was a shortage of tests and protocols for testing were not very clear as well. So we all knew that there were more people infected than what the official numbers said. And the idea is, okay, let's try to find out that proportion of infected which are not reported publicly. And it's what we have done is based on what I've called last class INAR models, integer autoregressive, the ones that are based on thinnings. I think I'm almost sure that changing that INAR basic structure to Ingarch would work and would work fine. The problem is that maybe estimation gets a little bit messy. So I need young people. I encourage the youngs in the audience to do the thing, because I think it's feasible, but well, we have to just try to do it. Oh, okay. So problem of underreporting is very, very common in any epidemiological thing, and even in social research. One of the examples I can present you has to do with the gender violence denounces. So that's not really a kind of thing doing with epidemiology, but with social research. Problem is that if you have an underreportation of the situation, then your inferences are biased. And I mean, imagine at the beginning of the pandemic, and you were trying to redimension the healthcare. Okay, if you have, I don't know, say 1,000 cases a day, it's not the same as if you have 3,000. So you need to know the guys that are not reported but are susceptible to need a hospital bed. And that's why it's important to have a good quantification of the amount of underreporting that is present in the situation. So why coronavirus cases were underreported? Essentially, at the beginning, because of the shortage of tests. And even now, the asymptomatic individuals, they are still there. And people don't always feel like going to get a test, at least not here. Because if you have a positive test, even if you feel fine, then you have to isolate yourself. And nobody wants to stay isolated in its room 10 days if you're feeling nice. So I guess that still there is a certain amount of underreporting. The other source of underreporting in this pandemic is the data management. I mean, the public administrations not always tell the truth, not always know the real numbers they are working with. So that depends on the country, of course. But well, that's another source of underreporting. Okay, so this was from a talk we did in the beginning. So we had this propaganda say that everybody said that things were underreported. Okay, so some years ago, we had a simple methodology for modeling underreporting in a very simple situation, because the series we were studying by that time were, well, it was the human papilloma virus series that we talked about last week. Well, that series is underreported, but the nice thing about that series is that it's quite reasonably can be considered stationary. So we began with that case, and when we did this paper that's published in Statistics in Medicine. And the thing is that the epidemiologists, the people that had the data on papillomavirus, said that they suspected that some 30% of the cases were not reported. And well, we got more or less the same percentage, so we got very happy that by that time. But when the pandemic began, I began to collect by hand the number of cases here in Barcelona that they came up in the newspaper. So every day I just wrote down the number of infected, the official number of infected, and I told Amanda, who was the one who had, by that time, she had all the R codes and stuff. And I said, Amanda, we should do this because these data surely are underreported, blah, blah, blah. And we began to do that, and then confinement came. And the only reason why us, well, 5, because there was somebody else in this coronavirus thing. Well, the 5 people involved with the thing didn't become crazy during the lockdown, the hard lockdown, was because we were just working on this. So, well, that's it. So let me tell you about the easy thing, the easy model. the original model. So we had a Poisson in R process, but we consider that process not seen. I mean, we have a hidden process with the Poisson in R1 structure, that is, it's the number of ill individuals at time n is an alpha thinning of the number of ill individuals at time n minus 1 plus Poisson noise with the fixed lambda, but then lambda can depend on time as well. But for that moment, lambda was fixed. Noise was independent of the number of ill people. And well, that's what we had last week. So this is an homogeneous Markov chain. Transition probabilities are just a convolution of the binomial plus the Poisson. And the way we reported the under-reporting is by saying, okay, with probability omega, you see less than the number of cases you have. So with probability omega, we see a Q thinning of the true number of positive cases. And with probability 1 minus omega, you see them all. Okay, this has certain identifiability problems when Q is 1 or Q is 0. Okay, so we let that apart. But apart from the problem of Q equal 1 or 0, well, Q equals 0 is that you just don't see anything. And we also have problems with omega 1 and 0, okay? So omega and Q represent respectively the frequency and the intensity of the underreporting. So what we really are observing is the thinning multiplied by Bernoulli, with Bernoulli of probability omega. And with probability 1 minus omega, we see the 1 minus the Bernoulli times the INR 1. So it's straightforward to see that the expectation of the observed series would be 1 minus omega times the expectation of the hidden process plus omega Q times the expectation of the X, because the Q expectation comes from the thinning, and well, that happens with probability omega. So it's quite easy. So the stationary distribution, as we said last class, for the hidden process.
I'm sorry, may I ask you, there is a problem with your slides. Well, can you make them, so can you just unclose, unset the slides and then set them again? Because now it goes, now it's okay. The page goes, okay, sorry. Okay.
So I leave them like that?
You were at this page, yes, I think so. Sorry.
But the previous pages were lost.
Yes, you can show them. Take some few minutes to come back.
Who should have said that before? Well, I guess the important thing is here. Where? Just here. We have the hidden process, which is a Poisson in R1.
Yeah, showed me.
Then the underreporting is just taken like this. With probability omega, you have a Q thinning, and with probability 1 minus omega, you see everything there is. And what there is the hidden process. So what we are interested in is to have a good representation and the likelihood of the Y's, well, with respect to the Xn's. Fortunately, since it's a hidden Markov model, it's very easy to to have the likelihood, because of it's a well-known problem. Okay, so the autocovariance and the autocorrelation functions of the hidden process are, well, like this. The autocorrelations are exactly as the autocorrelations of an autoregressive process of order 1. And the thing is how to compute the autocorrelations and autocovariances of the observed process. And that's just a tedious arithmetic, just by conditioning on the observations. And what we get is this ugly formula here that has to do with all the parameters, but not with the lag. So the structure of the autocorrelation function is a multiple of the structure of the autocorrelation of the hidden process. An ugly multiple, but it's a multiple. It's a damping of the true, well, of the autocorrelation of the true number of cases unobserved. Marginal probabilities are a mixture of two Poissons. With probability omega, you have the thin version, and with probability 1 minus omega, you have the Poisson that comes from the NR. So, and when Q is 0, then what we have is a 0 inflated Poisson. So from the Poisson mixture, we can derive initial estimations, very naive estimations, sort of method of moments, say. You just fit to the data a mixture of two Poissons, and then what you have is an estimation of omega, that the probability of being in one of the two mixtures, and the two rates, the rates of the two Poissons. So obtaining Q is immediate because we just divide these two estimators and then we get Q. And in order to estimate alpha, the alpha from the alpha thinning of the hidden process, well, we simply take or the autocorrelation of order 2 divided by the autocorrelation of order 1. Recall that the autocorrelation function is alpha to the k. So if you want to have alpha, then you divide alpha squared divided by alpha and you get alpha. And another possibility is using that what we said before about the autocorrelation function of the observed process being a multiple of the autocorrelation of the hidden process. So rho 1, the observed rho 1, would be this multiple of alpha. So we just fit a linear regression without intercept, and well, that would give us the constant, and then that gives us alpha. But this is easier. Just divide in rho 2 by rho 1. And finally, well, you just isolate lambda and estimate it from here. So this method of moments works okay, but it has the problems that method of moments always have. So better take maximum likelihood, but of course, you can use these estimations, these naive estimations, in order to launch the minimization problem in the maximum likelihood. In order to compute the maximum likelihood, recall that we are dealing with a hidden Markov model. So what we have is transition probabilities in the hidden layer of the chain, and then we know the emission probabilities, which are the probabilities of observing something given that the true value in that moment was the hidden state, each of the hidden states. So, well, the emission probabilities are just very easy to compute as well. And from that, and using the forward probabilities, Kolmogorov forward equations for the Markov chain, what we get is that we can compute the likelihood of the model, the likelihood of the observations, which are the y's, just can write it as a sum of those forward probabilities, and that's the way it goes. I mean, that's the way we compute the likelihood, and then just maximize it in the usual way. Okay, so we have the estimation of the parameters of the model, and then what we need is to reconstruct the hidden chain. And the usual way to do that is the Viterbi algorithm, which is highly used in hidden Markov chains. The idea is to find the chain that maximizes the likelihood given the observed series. So what we only have to do is to, you don't need the denominator because it doesn't depend on the x. So it's enough to maximize the joint probabilities. And well, that's the way the hidden series is reconstructed. Okay, so what we did in that 2016 paper was to reconstruct the case of the human papillomavirus, the ones we did in the last class without having to under-report, just did it usual way, but now we under-report them. It's very likely that papillomavirus is underreported because most of people that have it don't have any symptoms, at least not at the early ages of the infection. Then it can cause cancer, and before developing cancer, very uncomfortable genital warts, but most people really don't have any symptoms. So it's very likely to be underreported. So that's what we saw last time, the mean, the variance, it is over dispersed. So, well, we just used the naive approach in order to launch the maximum likelihood procedure. So initial estimates easily found. And then with those initial estimates, we just did the maximum likelihood estimation. And what we had was, well, it's a 0.52 thinning. So roughly half of the cases survive, say, plus a noise, a Poisson noise with a relatively small rate. And with very large probability, it is underreported. So well, that's what we had. Parameter estimates, standard errors that come from delta method, and well, that's it. And this is the reconstruction of the chain. So the most likely chain. And well, so far, so good with the stationary case. We had, we did some model validation. We used, I don't know why, instead of using Pearson residuals, we used normal pseudo residuals, which are the Pearson residuals, but instead of looking them in a uniform scale, just do phi minus 1, so they look like normals. So, well, we had the normal pseudo residuals, and if the model is adequate, then these mid pseudo residuals should behave like white noise. And well, what we had was that they do behave like white noise. And okay, so what happens? Well, the frequency, omega is close to 1, the intensity is also significantly different from 0, so the series is underreported. The hidden series has an average which is roughly the double of the original mean. So, well, and what we had was that only 38% of the total cases of infections were reported by that time. And in what I said before, that epidemiologists agreed with that, is that, well, they said that they were only seeing 30% of the cases. So, okay, fine. Model more or less coincides with the idea that the doctors had in mind. Okay, so that model was extended in the original paper to non-stationary series just by considering lambda varying with time, like well, an exponential. And we also consider that the omega, the probability of watching the full, the true number of infections or watching the thinning, well, that was modeled like a logit, that is a logarithm of p over 1 minus p. It's that linear function of time. And covariates were also included. Covariates were sinusoidal waves in order to take into account, in some examples, periodic fluctuations of the data. So, so far for the old paper. Okay, so now we come to coronavirus infections. This is highly non-stationary, so let's try to figure out what to do with this. These are different regions in Spain at the beginning of the pandemic. I liked showing this picture because here you see what I said about the public records. These green lines here are the cases in Catalonia during the beginning of the pandemic. That's from February 16, wow, a year ago, my God, to May, 24th of May. Well, and you can see here a number of negative cases. That's nice public records. Okay, this is what happened at the beginning of the pandemic in somewhere else, my home country. Again, but you see, when we had this this kind of lambda, this lambda is increasing. That would go for nice trends. That is not useful in something like this. It's not the kind of trend you're looking for. This is last week. This is what's going on here in Barcelona from October the 1st. And I guess I draw this picture less than a week ago. So should have put the date of the last. Yeah, it was 13. I did that on Friday. Yeah, I did that on Friday, I guess, or Thursday. So, well, that's it. That's what we are having here. Okay, so the thing is, how can we incorporate in the process something that captures that kind of shapes, the kind of things we see here, things that go up and down and stuff. And what we did is, okay, first approach is let's model the mean of the latent process varying with time. Another thing we can do, we did, is to say that the intensity of the underreporting also varies in time for two main reasons. One, because eventually we are getting more tests. So problem of a shortage of tests that was at the beginning of the pandemic should not exist anymore. And because most countries still have problems by delivering the data. So the data look periodic, but it's not because the illness is periodic. Not X is not periodic. Which is periodic is the way that data are reported. Here in Spain, most of the cases at the beginning, at least of the pandemic, were reported on Wednesdays. And why was that? Because everything that happened during the weekend was tested on Mondays. And the test took 2 days to give results by that time. So that's why Wednesdays we had those peaks. That was something that the doctor told us. I mean, we just said, why, what's going on? And the guy said, oh, this is the weekend effect. This is people that go to the doctor on Mondays because they spend the whole week feeling bad. And they say, okay, I'll go on Monday. And they go on Monday. And then the result comes on Wednesday. So, but that's not attributable to the latent process. The periodicity is in the observed part of the process. So that's why the omega was the one that was modeled as being periodic. Okay, but I'm concerned now with lambda, with the modeling of lambda. And in order to capture the shape of the latent process, of the mean of the latent process, what we did is take into account a very naive form of the SEER model. So we got the 3 differential equations relating the susceptible individuals, how do they vary over time, the infected individuals, and the removed individuals, either by because they recovered and don't get infected anymore, which apparently is not the case with this virus. I mean, people can get reinfected at a lower rate than before, but they can, or because just they are dead and they won't get infected any longer. So, well, we have the system of equations, and of course, here the interest is in the parameters beta, gamma, and then the number of the susceptible population. Okay, we can just, to simplify matters, just consider the affected people. That is the sum of the infected and the removed. So the number of susceptible individuals would be N, the total number of individuals, minus the affected. And what we want is a nice formula or approximation of this number of affected people in order to incorporate that information to lambda. Lambda will be the number of affected people at time n minus the number of affected people at time n minus 1. That would be our lambda. So, well, what we need is the solution of this simplified system of equations, but this system of equations is very easy. If we just replace the infected in the previous system of equations here. Oh, sorry. What we get is that the number of affected people can be written like this equation, and then the last equation is the same as before. So by dividing these two equations, we get that the rate, the derivative of the removed respect to the affected will have this form here only in terms of the affected. So R, this is a separable variable equation. So the solution R in this system is this logarithm here plus an initial number of recovered people that we can set to 0. So if we replace this in this equation, R, we replace R by this solution here and take a Taylor expansion, what we get, a Taylor expansion of order 2, what we get is that this derivative is this simple equation here of differential equation of order 2 that has this very nice form whose solution is the logistic function. So with an ugly constant, what we have is that we know a very nice approximation of the solution of that differential equation. So well, close to the origin, we get that. We can have the value at infinity, but we don't care about that. We just care about this nice form. And now take lambda, the expected number of the hidden process, and well, not the expectation of the hidden process, the expectation of the noise in the hidden process to be, well, the difference between these two things. So this is quite nice. So this grows exponentially up to some moment and then goes down again and decreases exponentially. So now we have a model with more parameters. Alpha, the logarithm of that ugly constant we had there. We have the K. K comes from here, from the equation. And we have for the underreporting omega Q or Qn if we agree that the thinning depends on time. So that's what we have. And again, parameters are estimated by maximum likelihood, and the likelihood again is computed with the forward algorithm. It's uglier than it was before, but it has the same form. The only thing is that at each step, each of the alpha k's in the forward algorithm now depends on a lambda, which is time varying. So if we do that, for instance, with the data we got from Sevilla in Andalusia, well, we had this is the lambda of the Poissons, the mean of the Poisson innovations look like that, which looks like we thought it would look like. And in that case, the model Qn was considered to be a logit, so it decreased like that. And what we observed that, well, we had the true observations were 2,489 observations, and the number of estimated cases was, well, 3,700, whatever. So the system would be overlooking 51% of the cases that really happened. If, of course, if the Viterbi estimation would be the true number of infectious individuals. So that's another way of saying that is only 66% of the cases were reported by that time. Oh, so that's what we had with the Seville data. You see, it's not exactly a convex hull, what we reconstruct, but well, sort of. And this is what happened in the Uruguay case by that time as well, which was worse. Of course, here it was terrible because we had these huge peaks, which again were a problem of reporting. These were bursts in some hospitals and things like that. Again, this is the reconstruction of what happened in Barcelona. Well, no, not in Barcelona, in Catalonia, by gender. Why by gender? Essentially because when the counts are too large, thus the algorithms collapse. So that's why I think that maybe instead of using inar, using INGARCH, maybe things can work better. I'm not really sure about this. That the amount of the number of cases, if the number of cases is large, it could be dealt with better with an INGARCH than with an INARM. I'm really not sure about that. But what can be done in a nicer way is to consider things more than autoregressive of order 1. Autoregression could be considered of order larger than 1. And maybe we should consider autoregression of order 5 or 7, which should be the latent period of the infection. Or maybe just take only one lag, but not the lag immediately before, but 5 moments before, or 5 or 7. I'm not really sure what would be better. Homework, you can do that. Well, what happened here in Barcelona immediately after lockdown looked like this. And this is not because we went crazy when they just let us out, but something worse than that. They let us out exactly one day before St. John, and St. John is the beginning of summer, and people here go to the beach and put up fires in the beach and dance all night and whatever. And then 2 weeks later, we had this peak here. Aren't we predictable? And it's disgusting. Okay, so model of Barcelona after lockdown, even with Lambda, was looking, Lambda was that exponential growing up and then going down. Well, when we did these computations, the thing didn't begin to go down yet. So we only had this kind of Lambda. And since we are here with that Wednesday problem, then we use for QN, we used a logit, but with covariates, with a sinusoidal covariate, to take into account that weekly ugly effect. Okay, so far the model works nice. And then comes the most complicated part of a thing like this, which is forecasting. I didn't say anything about forecasting last class. So let me say a couple of things about forecasting. There are 2 ways to forecast. The more straightforward way to do it, which is not the best, but it's straightforward, is okay, just try to predict the mean value of what's going on. So if you try to predict what happens at times n plus 1 plus 2 plus blah, 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 given the past observations, okay, we have 2 things here. We have the hidden process X and the observed process Y. So, okay, we have the Y's, and we can relate the expected value of the observations to the expected value of the latent process in this, it's just this multiple. So if we try to see what happens with the expectation of n plus k, well, just recalling that the expectation of xn plus 1 is alpha times the expectation of xn plus lambda, but lambda changes with time, then we just iterate this, and what we get is that the expected value of the hidden process, k lags ahead, well, it's alpha to the k times the expected value of xn, time this linear combination of lambdas. This is not problem because we have the lambdas and the alpha. So problem is, okay, we need the expectation of xn. Okay, xn comes from here. Xn is roughly like yn, well, the expected value of yn divided by 1 minus omega 1 minus q. But we can assume that the expectation of yn is roughly as can be approximated by the observation yn. Okay, so we have everything now. So now the expected value of yn plus k would be, well, one here comes from this xn, where we replace the expected value by this. So we get that ugly formula, but it's a closed formula. And the standard errors here are computed through a delta method. So you have to differentiate here with respect to everything, but it can be done. It's very easy. So that's for forecasting the expected values. Another way to forecast is using the conditional distribution. Okay, conditional distribution is a mixture of two components, which are essentially convolutions of binomials and Poissons, but a different binomial and a different Poisson in the two cases that we have, which is when with probability omega, we have the thing with the underreporting scheme working, and with probability 1 minus omega, we got the original non-underreported series. So what we have is that convolutions, that's again, that's nasty, but well, just replacing the parameters by the maximum likelihood estimates we got there, and we can find the quantiles of this distribution quite easily. So we have predictions. And well, what we have in these cases, what we really have here is, what are those? The paper, if I find it, I had the paper right here, but I have to teach this morning, so something happened with my paper. Lost it. Where's the paper? Well, I don't know. So I've lost the paper. Okay, well, what's that? Well, this first part, of course, is the dynamic prediction, the prediction of the past, say. Just take half of the data and point the average prediction. Well, this is the average predictions. The median is the yellow, is the median predictions. And the red lines are the quantiles. And these are the true predictions for the future. And well, that's it. By now, we should know what happens with that predictions. But well, okay, here we had this. So in some moments, the prediction of the past, say, this is the observed series. So by some moment, this escaped from the prediction lines, but well, it is what it is. Didn't escape that many times. So, well, this is what we had by that time. And well, this is all published in this +1 paper that I'm not really sure that I put the reference. Maybe I didn't. I should have. Ah, yes. The reference is down here, so it can't be seen. No. I don't know what happened. I thought I put the reference. Well, this is published somewhere. And another thing that can be done is to change the underreporting scheme. And what we did in the past, we didn't do this with the coronavirus stuff. We did it before with another example. Thinking that the underreporting can change from one state to another. I mean, some days you are underreported and some other days you are not underreported. This is quite artificial. I mean, underreporting should not work like that, but it allows to get more complicated autocovariance structures. So it's in the end, it's a trick. The interpretation that you are changing from one day to the other, from being underreported to being reported, that doesn't make much sense. But modeling the underreporting as a binary Markov chain, you change your state from being reported to being underreported just by jumping from one state to the other with certain probabilities. Well, that allows that the covariances of the observed process get more complicated, not just an AR1-like structure. And that's why we use this kind of underreporting. And well, it's what Zucchini and McDonald used to do in the whole book. So, well, again, we have the same latent series, and we have, again, the same sort of underreporting scheme for the observations, but now these indicator functions are not Bernoullis, independent Bernoullis, but are serially dependent. So what we have is a two-state Markov chain that gives us one more parameter. Fortunately, we only need to know only one of the new parameters, but okay, we have an extra parameter from the one we had before. Okay, this model, in fact, is 4 different models. If there is independence between the states of underreporting, we just had the previous model, the original model we had before. If there is no temporal dependence in the latent process in the hidden layer X, then what we have is that we don't have the alpha. And the dependence structure in the data is only due to the scheme of underreporting and not to the dependence of the latent process. Incredibly enough, we found a data set where this model is good, is reasonable. And of course, we can have IID data, which incredibly enough, they exist. So there's no dependence, nor in the hidden process, nor in the states of underreporting. So we have IID data underreported. This is this M3. Okay, hidden Markov model now is the same model that we had before with latent states, the observations, which now changed the name to Y to Z. I don't know why. That came from the paper, I guess. And we have, beside that, well, the Markov chain that says that in each moment we are reporting or not the data. Okay, again, expectations, variances of the observed process can easily be computed. Autocorrelation structure is more complicated because now the autocorrelation structure depends on the smallest eigenvalue of the transition matrix of the underreporting Markov chain, of this Markov chain here. So in that sense, this model allows more complicated structures for the autocorrelation. So when that eigenvalue is smaller than alpha, then the autocorrelation decreases geometrically at rate alpha, which is what we had before. But again, when we have higher chance of remaining in the same state of underreporting, where most of the time you are underreported, but eventually jump with small probability to observe the whole chain, then the autocorrelation decreases geometrically at a different rate, at rate lambda 2. And well, again, if lambda is negative, this lambda 2, the eigenvalues negative, and alpha is smaller, then we have again, the absolute value of the ACF decreases geometrically. So the ACF, in fact, is increasing. Okay, so again, how do we estimate? Okay, method of moments or maximum likelihood. Problem is that, again, when we have large counts, maximum likelihood becomes infeasible because now the hidden, the forward algorithm becomes more complicated and it's very, very slow, the procedure. So we had to estimate using the method of moments in places where there were really high counts.
Alejandra?
Yeah?
I'm sorry, I only see a part of the screen. Maybe there is a zoom, something like this, no?
Wow. Now?
No, this is still a part of the screen, but I don't know if it's the same for the other.
What do I do? Stop sharing and share again?
Yes.
Maybe.
Okay. Stop share and share again. Wow, now I've lost the screen. Where is it? Here. Now?
Now it is another corner, but it is still a corner.
Wow. Why?
I don't know.
I don't see your point. I don't see the problem.
Okay, so maybe it's me.
Is there some? Do the other have the same problem?
Yeah, I have one problem too, Thierry. Can you try with the full screen?
Let me try to share something different. Share my. Okay, let me share the desktop and see how it goes. What about now?
Actually, it is the same for me.
Same for me as well.
For me too.
Has this been happening all the time?
No, it's a few minutes ago. It changed. I don't know why.
What's going on?
But Lionel, maybe you can use your mouse to shift the screen. It works with me.
Me?
No, me. I mean, us. I can shift your screen, and then I see the whole picture. Now that's good.
Yeah, it's okay for me. Sorry, I can now.
And if I put it a little bit bigger?
Yeah, that's good. Thank you. That's perfect.
Otherwise, I can't read. Okay, so where were we? Well, again, we have this ugly thing now, but it can be solved more or less same way as before, except that we are having problems with the number of counts. So when we have the large counts, then we use the method of moments and otherwise maximum likelihood. And now the confidence intervals are obtained with just bootstrapping. It's a stationary bootstrap, Politis and Romano thing. You know how to bootstrap time series, right? You have to bootstrap by chunks.
Yes,
Huh?
Oh.
What? Pardon?
No, that was an error. Sorry.
Okay. No, well, the thing I was saying that bootstrapping time series is really nice. You have to bootstrap a whole chunk of the series in order to get stationarity. And what you do is you have to choose at random where you start uniformly in the data, and then choose a geometric number of points to see ahead. There's a delicate thing on choosing the mean of that geometric distribution, but once you settle down that problem, then you choose that number, and then you get that chunk, beginning, say, at x4 and of length 7. Okay, you put that 7 numbers, you get that block. And then, after that, you repeat the situation. Again, you sort where to begin, sort again a geometric with the same lambda, the same p, and okay, that new chunk, you just put it after the previous chunk ended. And that's the way Bootstrap works with the stationary time series. And that produces a stationary process. That's a result from Politis and Romano. Quite old now, I guess it's from the 80s. I'm not really sure the date of the paper, but it's a very nice paper. I guess it's called Bootstrapping Stationary Time Series or something. Okay, so we did that, then stationary bootstrap and get confidence intervals for whatever we had here. Okay, so, well, moment estimators are just fixed using EM to obtain the estimates of the mixtures. Now we can't use mixed tools, it's kind of more complicated. But then, well, this works. It's far more complicated, but it's just arithmetics. So, well, alpha can be computed. As you see, there is a closed formula for all that. So that can be Problem is that depending on what we have, the alpha is not, cannot be, might not be identifiable. So you need higher serial correlations in order that you have identifiability, because we have to solve an equation of degree 4. Well, and that's the thing. Maybe we need 4 moments in order to have a full identification, but in the end, you can find the alpha. So you have all the parameters. All the models work well with that, just using, again, the EM. And well, we had some stuff. Maximum likelihood estimation, again, can be computed the same way as before, but a little bit more complicated. Just have to assume that the process at the beginning was not underreported. You have to start the chain from somewhere. But since we are dealing with it doesn't change the results. If you assume that at the beginning the process was or was not underreported, the results don't change. And well, again, transition probabilities are, well, again, we need the transitions, the emissions, which are a little bit more complicated in this situation, but not that much. And well, that's it. We have an application for these 4 models. And we fitted all the models, and then the criteria for selecting the best one was just watching if the ACF, the auto-covariance function of the residuals were looked like white noise or not. And when the covariance looked like noise, just choose AIC or BIC in order to select between competitor models. And the latent series is reconstructed using Viterbi algorithm, same thing as before. And well, we had things like that. Things like what we had was where counts of the number of reports of judicial reports of violence against women in Galicia, northern Spain, northwest. And well, we had cities with large counts and smaller places with the smaller counts. See here, the maximum is 70 something, 80. And well, we had cities with larger counts. And well, we estimated the overall underreporting frequency. Here is this is the underreporting frequency, and here and at the right, the underreporting intensity. That's the Q. And we had all the possible models here. So and these areas were removed either because there were too small counts, or we didn't have over dispersion, so we didn't make much sense to use a mixture of Poissons as a final model for equidispersed data. And well, we had regions where we had the mixture of Poissons. That's model 3. So that means that we didn't have nor omega nor Q varying with time. No dependence in the underreporting, nor in time, nor in the hidden process. hidden process was IID. And the most complicated model was fitted in these regions. And here models had underreporting states, but serially dependent latent process. And well, we had data for everything. This data set gave us room for using all the models. And well, we can see an example of all the models and how the residuals behave. They behave more or less like white noise. And well, that's how the series were reconstructed in all the different things. So things worked more or less as expected. And well, I'm done, except that this has a lot of room for improvement. And well, how can this be improved? Well, by one way, using different thinning operations for the latent process. By considering innovations with other distributions, for instance, negative binomial. The thing is that we didn't need to use negative binomial because things with the Poisson case fitted reasonably fine. Instead of using thinning-based models for the latent process, I think that a good idea would be to make conditional regression, GLMs, in GARCHs. Another possibility is considering ARMA models for large counts and try to see how the underreporting works. Another possibility is to have a more complicated dependence structure in the underreporting indicators, but I don't think that would be such a good idea. I don't think we can gain much from that. I think that the best gain is for having, instead of the in R1 in the latent process, try to model it with a conditional GLM. And then that's my wild guess. But I guess I'm kind of old and tired now to attempt it right away. So if anyone volunteers, I'll be glad to help. And that's it. Questions? Anyone alive yet?
Thank you for the talk. Alejandra, I have a short question. I was wondering if you showed us that it's not so easy to find some kind of shape for the intensity or for the probability of underreporting. Did you try to? Yeah, so you mentioned several interesting modeling, but I was wondering if it could be possible to use a non-parametric method. So of course it will be difficult depending on the amount of data that you have.
Yeah.
Because you have this notion of local stationarity, which is more or less equivalent to fit the model locally using a sliding window. That is, you can take a restricted number of data and you make a sliding, and then you estimate and you try to identify some trends in the parameter, like the intensity of or the probability of underreporting. So do you think it's a good idea to identify some behaviors like this?
Yeah, but by yeah, a non-parametric regression on the original, on the data you see.
Yeah, I mean,
but that's why I think that the GARCH thing would do fine, because that would be the mean. You were be modeling the mean that way.
Okay, but
the mean of the whole thing, not just the mean of the innovations.
Okay, but I was thinking to, for instance, a model in which the probability of underreporting is time varying. So you have
okay.
You have a functional parameter, and you try to estimate it locally. That is, you don't at a
Okay.
time point, you only use a restricted amount of data. You know, just before and after this time point.
Okay.
Then you obtain a kind of local estimate. This is typically the idea.
And you do that by moving windows.
Yeah.
Okay.
And you try to see, but maybe there is no enough data for this. But
well, it depends. I mean, maybe you do have enough data.
Yeah.
I mean, we have a year for coronavirus. We have a year of data.
Yeah,
That's
a year could be a minimum, but it could be so.
You can do that with the small windows.
Yeah.
Small moving windows. Yeah. You see, you're younger than I am. You can.
No,
we can talk. We can talk about that. Yeah.
I know how to do it technically, but I have no the data. So.
Okay. Well, wow. You see, I think I am like the Coens film, Burn After Reading. I'm not really sure I have the data. Yeah, I do have the data.
Yeah,
of course, I have the data.
But if you're interested, we can discuss about this.
Yeah, sure.
I can just write some equation to suggest the modifications that I have in mind.
Do it.
Okay, thank you.
Yeah, thank you. Okay.
I don't know if there are other comments, so so thank you for the intervention of Mozart. And okay, I think we may maybe stop now. Or what do you think? What is your okay?
Well, thank you.
Okay,
thank you, Alejandra. Ciao.